Hi everybody. So this next chapter we're going to look at is chapter 5, and this will be on probability. This will be sort of a bridge chapter to some of the subsequent chapters. So, so far we've studied descriptive statistics. We've used statistics to describe things. Now we're going to move on to inferential statistics, where we'll try to infer or draw conclusions based on our data. And in order to do that, we will need to use some probability. So that's kind of what this chapter is for. So we're just going to pick up some basic probability from this section, and then we'll kind of move on to other things. So probability measures the likelihood of an event. It was started by Cardano, Pascal, and Fermat. Here are their pictures. It was motivated by games of chance. So here's some probability rule. This first section is on probability rules here. So these will be some of the rules. Apply the rules of probabilities. Compute and interpret probabilities using the empirical method, and compute and interpret probabilities using the classical method. So we'll see that there's sort of two different ways of doing this. Use simulation to obtain data based on probabilities, and then 5, recognize and interpret subjective probabilities. So let's look at each one of these. So probability is a measure of the likelihood of a random phenomena or chance behavior. Probability describes the long-term proportion with which a certain outcome will occur in situations with short-term uncertainty. Probability deals with experiments that yield random short-term results or outcomes, yet reveal long-term predictability. Long-term proportions in which a certain outcome is observed is the probability of that outcome. One of the important things that we'll use in this section is called the law of large numbers. And the law of large numbers says that as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome of observes gets closer and closer to the probability of that outcome. So an example would be maybe flipping a coin. So as you flip a coin, you would see that over time, hopefully over longer periods of time, that the probability of getting a heads would get closer and closer to 50%. Maybe you flip a coin and you get a heads the first time and then heads the second time, but you should see later on that you should get some tails. So in probability, an experiment is any process that can be repeated in which the results are uncertain. The sample space, denoted by S, of a probability experiment is the collection of all possible outcomes. So if you're dealing with, cards, the sample space might be the all the different combinations of hands you could have in a card game. An event is a collection of outcomes from a probability experiment. An event may consist of one outcome or more than one outcome. We will denote the events with one outcome, sometimes called simple events, by E with little subscript I. I'll just pronounce that E sub I. And general events are denoted by using capital letters such as E. And we'll explain this later in the next example. So let's look at an example here. Consider the probability of having 2 children, and identify the outcomes of the probability experiment, determine the sample space, and define the event of having 1 boy. So, so if you're having 2 children, typically you're going to either have a boy or a girl. So you can have a boy boy, boy girl, girl boy, or a girl girl. Right? Those would be the 4 possible outcomes. The sample space in this case then would just be what we have. Right? These are the 4 possible outcomes. And then the event of having 1 boy would be either you could have a boy and a girl, or a girl and a boy, right? And this is the event of having exactly 1 boy. Right? Now we're not going to calculate any probabilities in this experiment. We'll come back and do some more here. But if you wanted to calculate what's the probability of having a boy, exactly 1 boy, right? You would basically take this part C, the number of things here divided by the number of things here. So you take 2 divided by 4, which would give you a 50% chance of having exactly 1 boy. Okay, so objective 1, apply the rules of probabilities. So these will be some of the rules of probabilities here. And these may not make a whole lot of sense at first, but so we'll go through some examples. I think they're, in a sense, they're sort of self-explanatory. The first one is the probability of an event must be greater than or equal to 0 and less than or equal to 1. And then you can denote it by this. This is basically saying that the probability of something happening is between 0 and 100%, right? So you can think of 1 as 100% in this case. the sum of the probabilities of all the outcomes must equal 1 or must equal 100%. So you have to have that the probability of each event in the sample space, when you add them together, is equal to 1. So, if you've got something where you have a 20% chance of one event happening and a 30% chance of another event happening, and then if there's a third event, it should be 50%, right? They all have to add up to 100%. So those will be the basic rules we'll be using. So let's look at some other things here, and we'll come back and use these rules. But a probability model lists the possible outcomes of a probability experiment and each outcome's probability. A probability model must satisfy rules 1 and 2 of the rules of probability that we just saw, right? So all the probabilities have to be between 0 and 100%, or between 0 and 1, and the probabilities have to add up to 1, or in other words, 100%. So let's look at an example here. So here's what we've got here. We've got a bag of peanut M&Ms, and we basically sort the colors of the M&Ms into different categories here. And we look at the probability or the percentage of randomly drawing a particular type of M&M. So the question, is this a probability model, right? So the two things we have to verify then, just going back here, are all the probabilities between 0 and 1, and if you add the probabilities together, do you get 1, right? So if you take, if you look at the probabilities, these are all between 0 and 1, right? They're all numbers between 0 and 1. And so the question is then, if you add these together, do you get 100%, right? Which I think you'll see that you do, right? So that does equal 100%, right? So that is a probability model. Let's look at some other definitions here before we look at some other examples here. An event is said to be impossible if the probability of an event is 0, right? So the probability of finding, like a person living on the moon, I would assume would be an impossible event, right? As far as I know, there's nobody living on the moon. If an event is certain, or if it's, absolutely certain to occur, that event has a probability of 1, or in other words, 100%. An unusual event is an event that has a low probability of occurring, usually less than about 5%, or 0.005, but this can vary. But unless otherwise stated, an unusual event will be 5% or less. Okay, so that brings us to objective 2, which is on computing and interpreting probabilities using the empirical method. And so this is based on observation and experiment. Approximating probabilities using the empirical approach, the probability of an event happening is basically the frequency of that event divided by the numbers of trials in the experiment, right? So if you're doing some sort of experiment, let's say you're rolling dice, and you roll a 6-sided dice, and you notice that the probability of rolling a 3 comes up about 1/6 of the time, right? Based on this experiment, that would be an example. Here's another example. Pass the Pigs is a Milton Bradley game in which pigs are used as dice, and points are earned based on the way the pig lands. So there are 6 possible outcomes. So the pigs have a side with no dot, a side with a dot. The razorback should mean it would land on its back. If it lands on its snout, you'll get this frequency. So a class of 52 students rolls the pigs this many times, and these are the outcomes that they get. So use the results of the experiment to build a probability model for the way the pig lands, right? And estimate the probability that a thrown pig lands on the side with a dot. So again, basically just take the number of each thing in each category divided by the possible number of experiments. And then, this looks like all these are between 0 and 1, and I think this will add up to 1 if you do that, so it is a probability model there. And if you look at this, right, this is, for the leaning jowler, this is less than 5%, so that would be considered to be an unusual event. I think leaning jowler is when it lands on like one leg and then its cheek. Again, if you haven't played this game, you may not know what this looks like, but look up Pass the Pigs, and you'll see how this works. But the important thing, though, is that the probability that it lands on the side with a dot is given by this value in the table, and then a leaning jowler, right, would be unusual because it's less than 5%, which is how we're defining unusual. Objective 3 here then would be to compute and interpret probabilities using the classical method. So the classical method basically relies on the likelihood of things happening. It just doesn't depend on experiment. So it's a bit more based on sort of reasoning. And it's the number of ways an event can occur divided by the possible number of outcomes. And so, this does depend on some things that you'll have to know some information here. But let's say you take a fun-sized bag of M&Ms, and there are this many of each color candies in here. Suppose that a candy is randomly selected. What is the probability that it's yellow, right? So you don't need to do an experiment in this case. You would just add up the total number of bags of candy, and then just divide by the total. Right? So if you want to figure out what's the probability of getting a yellow, it would be the number of yellow divided by the number of possible bags you could get. Right? There'd be 30 possible outcomes you could get, so that would be 0.2. The probability of getting blue would be 0.06, and the probability of getting yellow, right, is 3 times as likely as getting a blue, right, based on what we saw. So objective 4 is about using simulations to obtain data based on probabilities. We probably won't be using this too much, but simulation can be accomplished using a variety of software. You can see page 268 to 269 in your book about that. We aren't going to deal with this too much because it requires some software, but you can basically use some sort of computer software to simulate an experiment instead of actually conducting the experiment. So the subjective probability of an outcome is the probability obtained on the basis of personal judgment. So for example, an economist is predicting there's a 20% chance of recession next year would be subjective probability. Maybe this is based on some sort of empirical data, but things like that are really, really hard to predict. Just to give you another example here, let's say in the fall of 1998 article in Chance magazine, Hal Stern investigated the probabilities that a particular horse will win a race. He reports that these probabilities are based on the amount of money bet on each horse. When a probability is given that a particular horse will win a race, is this empirical, classical, or subjective? So again, it's not really empirical because it's not necessarily based on experiment, right? I mean, I guess he's using past information. It's not classical because you don't really have any definite answers there. So this is subjective, right, because it's based upon people's feelings about which horse will win the race, right? And the probability is not based on a probability experiment or counting equally likely outcomes, so it's neither empirical nor classical. Okay, well, I hope that clears things up. I think that should finish up section 5.1. I guess we'll skip this example here. So the next thing we'll look at here is section 5.2 on the addition rule and complements. So like usual, if you guys have any questions or anything, let me know.